up about 70 people joining us. And ironically, that's about the number of presentations that we have today at the 8th Annual Research Day, Lawrence Technological University. So you can see here on our share screen that I'm showing you that after Dr. Moschelli's keynote address for the Presidential Colloquium, we would really like you to visit the actual Research Day webpage. So please just type this in your browser, very simple link. And on the Research Day webpage, you will see all of the student and faculty presentations. And this year we have about 70, which is really amazing because students and faculty have been contacting me all semester, struggling due to our need to be agile and accommodate the pandemic and our concern with student safety. And particularly in the last couple of weeks when students and faculty were scrambling to finish lab projects, but we got them all together. And as I said, we have about 70 presentations, and that's really awesome. And so for the faculty who are joining us today, I would really appreciate it once you visit the Research Day webpage, if you will register to be a judge for the poster competition that we have. We have 29 specific undergraduate posters that we would appreciate you taking the time to judge. And you can judge this at your leisure using the form. After you register, you'll be sent a link, and would appreciate it if you could get the judging done by Sunday. So without further ado, I want to pass it over to Dr. Modgill, who will make an introduction, and then Dr. Sobe will introduce our keynote speaker today, Dr. Moschelli, and then Dr. Moschelli will give us his keynote address. So thank you very much, everybody, and I hope you enjoy the rest of the day and enjoy the Research Day today. Thank you. And by the way, this is the only live event. Everything else on the webpage is asynchronous, so you can view it at your leisure. Thank you very much. I turn it over to you, Dr. Modgill.
Thank you, Matt, and good morning, everyone who's on the line. And Matt, also, let me first thank you and your team that put together this program all these years. It takes a lot of work to assemble information and make it presentable to the whole campus. So thank you for that. And for everyone, I'm so very pleased to add my welcome to all attendees for the 8th Annual Research Day. As you may have known or heard that we started this tradition in 2013, a year after I joined this great institution. I still remember the day I came here, first day, I spoke with Matt, and he says, "What are you going to do for research?" I said, "We're going to just wait. We're going to do some great things. And I want you to work with me and we'll set up something great." And that is a tradition that we have now established to honor and appreciate our student, faculty, and researchers for their work to be presented not only here, but nationally and beyond. Because now we have researchers, undergraduates presenting on national meeting. This was unheard of before. So I salute all of you who are participants and those who are listening, that we are evolving as an institution in more than one way. Research was seen at in Oakland County, and there were only 1 or 2 universities that did that. We were very well known for applied work with the corporations, but there was not much emphasis on basic research or externally funded research with NIH or NSF. We have it now. So we are evolving. We have emphasized that it is the research and innovation that make an institution a university. If we don't have research, then we are a community college. So I think this is a healthy change. Last year, we were not able to join our colleagues for Research Day because of pandemic. I hope everybody understands that it was just not possible or appropriate. On the Research Day every year, we also celebrate faculty excellence and their work with student researchers, saluting their research and innovative entrepreneurial works. Each year, a panel decides on selection of a faculty member from one of our 4 colleges as the speaker for the presidential colloquium for the reason we are gathered today. This year, we have an outstanding researcher from College of Arts and Sciences to present his noted work. We, as a legacy institution, were noted for some more faculty doing industry-sponsored research or work, I would say projects, not necessarily research, but it's projects that led to some research in the area of their expertise. But the fact is we have a great platform and always had and now more active of both research in basic and applied research on this campus. Many of our faculty are funded externally for their innovative proposals, while other work with corporations doing research to solve problems. So we have a treat for you today to listen to one of our top basic researchers whose work is funded externally by National Science Foundation. Those of you who do not know much about it will eventually know it if you stay in research. National Science Foundation is known for basic research. If you have a clinical research that involves human or medicine related topic, then you go to NIH. The basic science is very hard to get. It actually, both are difficult, but basic researchers in NSF, they have to score a lot higher to get a research grant. So I really honor and salute our speaker for getting National Science Foundation grant. It's difficult to win, but it really depends on how good you are and you have it. So needless to say, I am very proud of George Moschelli, who's our speaker this morning. And we will have time from our Chief Academic Officer, Dr. Tariq Zohb, like many of you have met, and to introduce our speaker of the morning. I hope you have a great listening, and I hope you learn also. And I will urge that you feel inspiration from the lecture in whatever area you're working, because knowledge is gained to be distributed. Anyone who has the best knowledge in the world doesn't share, goes with him and nobody knows about it. So publication, presentations are medium which help other people get inspired and follow your lead. With that, I thank you and I hope we have a great day listening and also following this work. Thank you, Matt, and thank you, everyone.
Thank you, Dr. Madgill. And now I'd like my pleasure to introduce our provost of Lawrence Tech, Dr. Tariq Zohb. Thank you, Dr. Zohb.
Thank you, Matt, and thank you, Dr. Madgill. First of all, I'd like to express my thanks and gratitude to all of our wonderful researchers, our senior researchers, our faculty members, and our junior researchers, our undergraduate and graduate students. It's a pleasure being here and just reconfirming what Dr. Madgill has mentioned. LTU is truly an emerging research university. And I am personally looking forward to amazing outcomes in terms of intellectual merit, broader impact of the research that we are undergoing at our great institution. Without further ado, it is my great pleasure and honor to introduce our presidential colloquium speaker of the day, Dr. George Moschelli. Dr. George Moschelli is an associate professor of physics in the Department of Natural Sciences within the College of Arts and Sciences. George is a theoretical nuclear physicist whose research focuses on the study of the strong nuclear force and nuclear collisions at highly relativistic speeds. His theories and models support the missions of multi-billion-dollar international experiments at the Relativistic Heavy Ion Collider at Brookhaven National Labs and the Large Hadron Collider at the European Organization for Nuclear Research, CERN. George's work on modeling quark gluon plasma, one of the earliest forms of matter produced by the Big Bang that created the universe, and by the little bangs created by nuclear collisions, earned him a prestigious NSF Foundation grant and award in 2019. It is a great honor to be able to receive basic sciences grants from the NSF, as Dr. Madgill has mentioned. Undergraduate participation is a priority of George's research agenda. His research assistants learn computational methods for solving equations, creating simulations, and analyzing huge data sets. allowing them to contribute to state-of-the-art, high-energy nuclear physics research while simultaneously developing skills for countless applications in society. George also provides genuine research opportunities inside the classroom as part of the College of Arts and Sciences Course-Based Research Experience CRE program, funded by the Howard Hughes Medical Institute. These achievements and other active learning pedagogical innovations earned George the Henry B. and Barbara J. Harold Excellence in Teaching Award in 2019. George started his career at LTU by earning a bachelor's degree in physics in 2003. And you see the background on George's screen, a true blue devil right from the start, before returning as a faculty member in 2014. In 2010, George earned his PhD in nuclear physics from Wayne State, which was followed by a postdoctoral research fellowship at the Frankfurt Institute for Advanced Studies in Frankfurt, Germany. Please join me in welcoming George. We look forward to a wonderful presentation. Thank you very much.
Thank you. Thank you.
Thank you, Dr. So we turn it over to Dr. George Moschelli. Thank you very much.
So you can see my screen all right? All right, so first to mention the logo behind me, I guess I forgot that I always have this up on my Zoom. This was actually my concept art for our Society of Physics Students logo. And I thought, you know, we're the Blue Devils, but the real devil on campus is the goose. And I think everybody knows about the geese that are on campus. And so I think the goose, if we're going to rebrand, it's my pitch is for the goose on campus is the real devil. I'd like to thank many people. I'd like to thank Matt for organizing Research Day, as he always does. I'd like to thank my dean, Srini Kambampati, for putting my name forward for this. It's a great honor, and thank you for doing that. And yeah, so as both the president and the provost mentioned, this work is funded by the National Science Foundation. But there's also many other ways that we get support for money. And I'd like to also point out Keen. So thanks to the colleagues in engineering who have built this relationship with Keen, where I actually don't have the Keen grant. It's actually Pujo Bhattacharya, who's one of the other physics faculty who has the Keen grant. I'm just a co-PI, but we're still getting money for pedagogical activities from them. And of course, Howard Hughes in the CRE program. And I see that former Dean Xiaoping Moore is in the audience. And I think we all have her to thank for getting that started for us. So what I'm going to talk to you about today is both a kind of an overview of the problem that I'm working on, which is relativistic nuclear collisions. And so you can see this picture that I have on this slide is one of the first event displays of a nuclear collision event by the relativistic heavy ion collider. This was around circa 2000, and this is the collision of a gold nucleus hitting another gold nucleus. And each one of these colored lines, so these things are colorized, but each one of these colored lines is a particle that's produced in the collision. And this shape that, like in white, that outlines it, that's kind of like a schematic of the detector that's measuring these lines going through space. So my job as a theorist is to take these lines and try to explain what's happening in the nucleus and the physics of the collision with what's going on in the background. I get a lot of help, obviously, like the experiment. You know, they're the ones who take these lines and tell me some information about them. But then it's my job as a theorist to explain why. And I'll talk more, obviously, about this as I go on. But I think also President Modgo and both Provost Soap mentioned that the NSF funds basic research, but it's very, very important to mention the broader impacts of that research. And that's another thing that I'm gonna focus on in this talk. So, and before I begin, I'd also like to very much thank the other physics faculty. And I think I put them here in like ascending order of seniority here at the university. And I really want to thank all of these people because I can't do research without their support. And I haven't grown as a teacher without their support. So I really like to thank them. I'm like, so Scott's epic beard, I think everybody knows Scott. Scott's epic beard in this picture. I don't think he has this beard anymore, but I vote to bring it back. And I think also someday soon, you're gonna see Bujo here giving this colloquium again, because he's also funded by the NSF, and of the 5 of us doing physics, 2 of us have NSF grants. And I think that's amazing. And he's also the one with the Keen grant. So you're probably gonna see more physics from the College of Arts and Sciences pretty soon. Okay, so in order for me to talk to you about what I do, I got to give you some background, and so we might as well just go all the way back, right? All the way back to the history of the universe and the Big Bang. So this is obviously a schematic of the Big Bang, and these numbers are pretty approximate, but I think we're getting them down to less than the 20% error range, which you might think is a big error range, but it's still a big achievement. And so we don't know what happened at the Big Bang, but just after it, we do know that there was this rapid inflation phase. We call it the inflation phase because the universe expanded very quickly then. And I can't say that we know what exactly the matter was there. Probably have a pretty good idea that it was some combinations of the fundamental forces, but we can't really say for sure. But at some point they formed, on this thing it's listed as quark soup. What we call it in the business is quark gluon plasma. And this quark gluon plasma lasted to about 1 second in the age of the universe. And this term freeze out generally means when we start having the ending of the interactions between quarks and gluons, and we start talking about interactions of the particles formed from quarks and gluons. And I'm going to explain more as that goes on. And then as this, the universe expands and cools, and you start forming nuclei and then forming atoms, and then those atoms start clustering. And about the age of 300,000 years, this clustering is starting to happen where we're getting close to the point where the forming of new stuff, in terms of atoms, is ceasing, and things are, at least until fusion starts happening. So this is like before fusion is happening, but the universe is now big enough that parting company here is intended to mean that the interactions over the long distances of the universe are so far that they're pretty much only happening by gravity, and the time it takes for an interaction to happen from one side of the universe to the other side of the universe is now becoming long enough that it's becoming that really only gravity is going to be doing it, or and light's obviously traveling, but light's not going to be influencing the formation of things at one side of the universe to the other side of the universe. And so I'm going to stop sort of the explanation there, because where my research stops is at this 1 second. What's happening in this quark gluon plasma phase? And I sometimes have this joke that I'm studying the earliest matter of the universe, the first matter that was produced in the universe, and the transition from quarks and gluons to what we now know as matter. So I'll tell you more specifically the way that we study these things is I'll try to start it from where I think everybody kind of knows. Everybody knows an atom exists. And this picture of the atom is actually not really what atoms look like, but it's a schematic. It's kind of got what we got. Electrons are orbiting a nucleus, and these electrons are the particles that are in our electrical currents. When we say electricity, we're talking about electrons. The things that make all of our electronics technology, they're pushing around these electrons, and they're orbiting around the nucleus of atoms. The orbits don't work kind of the way they're drawn, but that's a detail for a different talk. I'd like you to take a look at the scale. The scale of this is that an atom is 10 to the minus 10 meters, and the nucleus is 10 to the minus 14 meters. So to put that in some kind of perspective, if you were the nucleus, like if you were the size of the nucleus, then the size of this atom would be like 6 miles, right? 10,000 kilometers. So most matter, everything that's made up is mostly just empty space. The nucleus is a very, very tiny part of the atom, and the atom is very big and mostly empty, depending on how you talk about what the orbitals of these electrons are talking about. So, okay, this is atomic physics. This isn't where I'm at. I'm at nuclear physics, which is this end. And in the nucleus, there are two types of particles that's in normal matter: protons and neutrons. And the protons are the ones that determine what element we're talking about. So the more protons there are, the higher you go up on the periodic table. So this is the thing that determines what element we're talking about, and the number of protons is exactly the thing. And the number of neutrons is kind of about how stable the nucleus is. So the difference between a radioactive nucleus and a not radioactive nucleus is often the number of neutrons. And again, that's a whole different talk that we're just gonna pass by. And so now the protons and neutrons inside the nucleus, those aren't the smallest things either. Inside the protons and neutrons, this is where the quarks are. And right now, this is the level of our understanding. If there's something that's inside of a quark, then we haven't found it yet. And these quarks have colors, which I'll talk about in a bit. But if you think of the electric force, everybody I think knows has a positive and negative force. Well, the strong nuclear force that governs the quarks and holds the nucleus together, there's three charges. So the electric force has one, the strong force has three, and we just label them with colors to keep track of them. So red, green, and blue are generally the colors, and the theory of the strong force is often called quantum chromodynamics because we named them with the three colors. So we're going to be talking about these quarks and how to study them and the problems with studying them. And you can see now they're like the electron, as far as we know, one of the fundamental particles of nature. And again, as far as we know, there's nothing inside of them making them. So let me give you kind of a list of the fundamental particles that we know about. So there's 6 quarks here in this lavender color. And the quarks that make up protons and neutrons, which make up the nuclei of atoms that make all matter, it's just these first 2 quarks, the up and the down. And to make a proton, they come in groups of 3. So 2 ups and a down is a proton, and a neutron is two downs and an up. And they all have these funny names, and they all have these funny quantum numbers. Like, so up and down, again, just more or less arbitrarily chosen. The next one that was discovered is the strange quark. And it's literally given the name because we were doing I say we as in the royal we of physicists, doing experiments, seeing the particles that come out of collisions. And there was particles that just had these properties that were strange. So let's call it the strange quark. That seems like a good enough idea for names. And then you started hitting it with the math, right? You start hitting with the math to try and explain it. And I'm not joking that there was like a line that was like, if we had another quark, it would fix these problems like a charm. And lo and behold, we found another quark and just named it the charm quark. So, and notice that, the charm quark is, the masses are listed here in kind of small numbers, but very, very heavy. So very, very rare to produce. And then again, hit it with more math, start doing some group theory. And the group theory predicts that there should be 2 more quarks. And indeed, we did find those 2 more quarks. The top and bottom quarks, even more massive and even more rare. And I think it's even funny that these used to be named Truth and Beauty. So they got switched to top and bottom because they already had like the T and B labeling them. But they used to be called Truth and Beauty. Again, brilliant naming by us. I guess we can't really claim that we're all that clever when it comes to that. So those are the quarks that make up when we call hadrons, which is things made of quarks. And there's 2 ways that happens. One is the proton or the neutron or things like that have 3 quarks. We call them baryons. And there's also the version where there's just 2 quarks, a quark and an anti-quark. And you can see now this one's labeled with the anti-color of blue. So there's, if you think of the electric force as having one charge, the electric charge that's plus, and an anti-charge that's the minus, The strong force has 3 charges and 3 anti-charges. So you can see that this starts to like build up in complexity, which is why every single one of these things I'm telling you is a talk on its own. There's more particles in the fundamental particle list. The ones in green here at the bottom are called leptons. The electron is our buddy that, you know, basically all of our chemical interactions and all of our electronics interactions are all working with the electron. There are different versions of the electron that just have different mass. So the muon and the tau are both like just the same as the electron, but they have different masses. It turns out that recently there was a new experimental, well, I can't call it quite discovery yet, but a release that's just barely not at discovery level, where the muon has some different properties that aren't explained by the theories that we get from starting with the electron. And actually, if you wanna know more about it, I really suggest that you contact Dr. Bhattacharya. Like, I think they released this new information like as a blind study release, and then you give out the number, and then I think he stayed up all night trying to explain it and writing a paper and submitting a paper about it. So you should ask him. Each one of these electron-like particles comes with a partner that, again, a whole another talk I won't talk about, but these are the neutrinos. And then the other important group are the ones here in kind of like this salmon color, which these are the particles that carry forces. The one that we're the most familiar with, but maybe don't know is a particle, is the photon. It's a light particle, a particle of light. It carries the electromagnetic force. The version of that particle for the strong force is called the gluon. So because it's the glue that holds the quarks together. Another inventive name. But yeah, so this is the particle that carries the strong force. It has a color charge. So it transfers color charge between the quarks. And so this interaction of this gluon with these quarks is essentially the thing that I'm trying to study. These other particles that carry the weak force, I'm again not going to talk about, but there's a force that governs the changing of particles from one type to another type. Like, and these particles are usually the ones that are involved in that. And then, of course, the most recent particle that's been added to this list is the Higgs boson that was discovered by the LHC only a few years ago. Again, whole other talk, not going to talk about that one. But this one is responsible for giving the masses to these other ones. But I think that's the end of that one I'm going to talk. What we want to focus on are the quarks and the gluons that are held in these baryons and mesons, and we want to get access to them to study them. That's our goal. So a few more words about the difficulty of studying quarks is that on the left here, I have what's known as the electric dipole, which is a positive charge and a negative charge near each other, and they make an electric field. We know about this very well for many, many years. You know, this is the shape of the electric field in these black lines. And this electric field goes out to infinity and gets weaker and weaker as it goes out. But this is the shape that it's made by two electric charges near each other. And at a quantum level, it's governed by what we call quantum electrodynamics. For the strong force, we have to use these color charges, but the gluons have a problem. The problem with the gluons is that gluons also feel the force of other gluons. So the field that's created by the gluons is very contained. It doesn't spread out to infinity like the electric field. And it's this field that would connect the interaction between two quarks. And we want to understand how this field works. We call this the quantum chromodynamics, which, because now it's talking with the quantum mechanics of the strong force charge, which is the color charge. And I did a little quick back of the envelope calculation with the strong force in place to separate two quarks by 1 femtometer, that's 10 to the minus 15 meters. To separate two quarks by 10 to the minus 15 meters, it requires 16 metric tons of force. Like if we were using the gravitational force, it's the force equivalent to lifting 16 metric tons. So this force is when I say the strong force, again, we just picked the name. It's very strong. So we'll call it the strong force. The problem with the strong force then is that it's so strong, you need a lot of energy to pull quarks apart. And what if we want to study quarks, we got to try and pull them apart. If we put in all of that energy to try and separate the quarks, it actually turns out there's enough energy there to just create new quarks. So anytime you try and pull them apart, you have to put in so much energy that you can just create new quarks that then keep the quarks paired up with a different partner and still be bound together. This is one of the fundamental problems of physics right now that we don't know how to overcome. And so anytime you try to study quarks, you'll always have to study them bound together with other quarks. So you can only study them at the particle level rather than the quark level. And this is one of the fundamental problems of studying the strong force. But it turns out that if instead of trying to pull them apart, if you try to push them together, then the strong force actually gets weaker. This is another unique thing about the strong force. If you try to push the quarks together, the strong force gets weaker. So that's our goal then, right? So that's why we do nuclear collisions, because nuclear collisions takes a bunch of quarks that are sitting in a nucleus. So like this is like a picture of a loosely packed nucleus with a bunch of quarks in it, filling up the protons and neutrons in the nucleus. And instead of pulling them apart, we want to push them together. So when you push them together, two things happen. You heat it up, but if you heat it up, that's the same thing as like trying to separate the quarks. You add the energy to the quarks, and so then you actually start producing new quarks. But the collision also compresses them. So at this point, if you can compress all of these protons and neutrons together, such that you can't really think of the borders anymore as like, if I pick one quark, I can't tell you like which border it came from really. So they're all overlapped and close enough together that the strong force from the gluons is getting weaker. And essentially now you have to erase the borders and think of all these quarks as a fluid. That's essentially the model, or at least a gas of these particles that are kind of like tightly packed. And so the strong force goes away, and this is what we call deconfined. And so now the goal is to study this quark gluon plasma. This is what we call it. We have to study this bigger system that has lots and lots of quarks together that are very hot and very close together, so that we try. Now the goal is then model it like it's a fluid or a gas. And by the way, the temperature at which these quarks then now, obviously they're very packed and very hot. So that's why there's going to be the explosion. And this explosion is the explosion we call the little bang. And as this explosion expands and cools down, there's a transition where these quarks are no longer close enough together to be just quarks on their own. They start forming particles again. And the temperature where that transition happens, I think, is also one of the marvel measurements that we've made with our experiments, is at a temperature that's about 130,000 times hotter than the sun's core. So that's also kind of impressive to think about. And then this thing is just going to keep expanding as it cools down and form particles. And then the particles come out, and we want to measure them and try to get information about what happened when they were in this phase. So this is a schematic of the process of the collision. So if you imagine two nuclei flying at each other, accelerated by some accelerator, because of relativity in the lab, they're going to look all squashed like this. So kind of like two pancakes hitting each other. And then they hit each other, and this is the initial moment of the collision. And energy starts getting dumped into the vacuum, probably in terms of like very strong gluonic fields or other kinds of electromagnetic fields. And then there's the rapid expansion phase that's just like the inflation phase of the universe, but on a obviously much smaller scale. So these nuclei are going so fast, they smash through each other and then just keep going and sort of like stretch the fields out in between them as they separate. So during this phase, there's like this rapid expansion, and quarks and gluons are forming, but they're forming like in very complicated and random, unpredictable ways. So there's huge fluctuations. So this is kind of the first moment where I enter, where I'm trying to understand how do you take these fluctuations that should be there at the beginning and measure something at the end that shows you that these fluctuations were a certain way, and that has to do with the strong force. So the way that we generally try to do that is we think about it as being a gas or a liquid that's trying to go from highly non-uniform to something that's more uniform in temperature and density, and that and then at some point it reaches that critical temperature and starts to switching from quark gluon plasma to particles, and it continues to expand, and the forces between the quarks are driving it towards like a thermodynamic equilibrium. And this is the thing that mostly I'm trying to model, is this with usually with hydrodynamics, sometimes with kinetic theory of gases. How do you model start the initial state? What does it look like? How does it move through all of this dynamical process of going towards equilibration? And then at the end, there's particles that get measured by a detector. And whatever the patterns in these particles are, can we use those patterns to match up to my theory? And does that theory then tell me something that goes all the way back to the beginning? And even the particles at the end, what we really see is this, right? The detectors just see particles that come out of the collisions. They can measure their momentums. They can measure their charges. Sometimes they can measure their masses and get a total energy, and that's about it. So it's kind of now this like trick of this game of what particles do I measure? How do I connect it to the theory? And then what does the theory tell me about the strong force? That's kind of the gist of what I'm doing. And so let me just give you a result. And like, I'm a theorist. I can't help. I can't give a talk without showing an equation. You don't have to know too much about this equation. You just kind of look at it like it's a picture in itself. But this is an equation that I worked on with my collaborators for the diffusion of correlations between different points in the fluid, so that when we see the particles coming out, we can match them up to that correlation. And the two things that were innovative in this calculation was we wanted to make this diffusion causal, which is the problem with diffusion is that the mathematical definitions, the mathematical derivations of it generally ignore the fact that you can't go faster than the speed of light. So we had to restrict the normal way of talking about diffusion to be causal, meaning it can't happen faster than the speed of light. And also we wanted to use this equation to talk about the fluctuations between the different points of the fluid. We want to understand the random processes and how do those random processes get smoothed out. So there's two part, like we're comparing the positions and fluctuations of two particles in this equation. But really just to point out like kind of what's happening, what is diffusion? Diffusion equation looks something like this. If you've seen diffusion in your life, I'm sure, if you imagine that you put a drop of dye in a still glass of water, and you didn't shake it, the dye starts like very concentrated in the spot where you dropped it. And then eventually, because of the random motion of the molecules that are in the water, the dye spreads out. And eventually the whole water has some uniform color. That's the diffusion process. And the problem is that takes time, and the diffusion calculations usually allow particles to move distances that are too fast for the speed of light. So we tried to solve that problem. And the way that problem got solved when we got this equation, it turns out that this equation is very much like a wave equation. So like think about a wave traveling on a string, right? There's a bump that represents a fluctuation or some kind of density in the material, and its interaction with the material gets transferred through the material like a wave down a string. In this case, there's two bumps that sort of spread out, and the speed at which they spread out is the speed of sound, and that's sort of in this equation too. So the two things that are happening in this equation is really just a combination of diffusion plus wave behavior that makes it causal, but it's also for correlations as well, correlations of two particles at two different places. So this is the point in the talk when everybody starts thinking, what is anyone ever going to do with this? And I have to say that So first of all, this result was an important result for me career-wise. It got me a lot of talks in a lot of countries, even like around the world. But so it's hard for me to like give a talk about what this is the equation pretty much got me this NSF grant. But at this point, people are like, oh, okay, this is like a lot's going on. What are we ever going to do with this? Um, I have to say that I get a little defensive about it, and I always think of the same thing. Every time I've given a public talk, I get this question, and I think in my head, I never get to say it, but now I get to say it. Is I always think of those people as like an Ebenezer Scrooge like type character holding a candle in the 1800s and saying to James Clerk Maxwell, who's the person who combined these equations on the right. You can just look at these equations like they're a picture. You don't have to understand them. But these equations govern how light moves in space. They govern how magnetic fields and electric fields interact. And we use them for all kinds of technology, right? Like antennas work because of this. Generators work. Electric motors work because of this. Uh, all kinds of our wireless charging for our phones works because of these equations, right? These equations are about light, and I always think of this Scrooge character holding a candle, saying to James Clerk Maxwell, like, what are we ever going to do with this? And what is Maxwell going to say? He's going to say, well, 100 years from now or 150 years from now, there's going to be this thing called the induction cooktop stove. It's not going to catch on, but we can get one of those. But you know what else is going to catch on? The microwave. That's going to catch on. Everybody's going to have one of those. Uh, there's no way that he can know that. And this is very theoretical work that you can see even from the dates here that took over 60 years to develop. And that was 150 to 200 years ago from now. And we're still using these things to develop new technologies. This is kind of the place that we're at with basic science. And this is kind of a meme slide, I get it. And to not be, memes are always a little bit disingenuous. So, for example, to develop the light bulb, it wasn't that, we needed these equations. We needed other things as well. We needed things like, how do you make thin tungsten filaments? We needed things like, how do you make a vacuum tube? And we needed good batteries. We needed chemistry and things like that. So it's not like these equations themselves make stuff happen, but also it's not like stuff doesn't happen without these developing along the way as well. So I kind of am going to make the rest of this talk like, we're the new versions of Ebenezer Scrooge. Instead of holding a candle, we're holding our phones, and we're thinking about the strong nuclear force, and we're going to say like, what is anybody ever going to do with that? And it could be that 150 years from now, which I if I were a betting man, and I am, that the technology we're using is going to be based off the strong nuclear force, and then the next person who's talking about the next thing is going to be talking about, you remember when they had these phones that worked on electromagnetic waves instead of the strong force? And that was 100 years ago. That's kind of where we're at. So we're all kind of the Ebenezer Scrooge, and I'm going to try to spend the rest of the talk teaching you the true meaning of Christmas here, except Christmas is basic science. And I want to talk about what's the value. Like, there's some value of even my equation. I could show you some parallels. So if you just kind of like look at how it looks, I can compare it to the engineers might look at electrical engineers in particular might look at this equation and see something that looks very much like what's called the telegrapher's equation for voltage in a transmission line. It has very much the similar form. The difference between my equation is that I'm trying to get fluctuations between two particles, so I have two space derivatives in mine. But there's the second time derivative that helps solve the problem of the time it takes when you move down a transmission line. And so there's just the mathematics of this already has already been shown to have applications in real world engineering problems. And I'd like to point out that the thing that you can't see from this equation is that what's built into it are these methods for for doing the calculus with random processes, or so we call stochastic processes. And that mathematics is used in finance. So this equation doesn't look anything like my equation, but I put it here because it's become famous recently, the Black-Scholes equation for fluctuating financial option prices versus stock prices. It's the math that you use to get my equation is very similar to the math that you use to get this equation. So you might not think, okay, we're going to have a talk about the strong nuclear force, that we would hear something about finance, but it really does apply. And interesting historical note, in the 90s, America was building was known as a superconducting super collider. And it was going to be bigger than any of the colliders we even have now. And it was going ridiculously over budget. And I think even if it were to double its projected budget, that was an underestimate but they actually started working on it before it got stopped. They were digging the tunnel and everything. So when that happened and they stopped the project, there was a bunch of physicists, high energy physicists and people who work on collisions that were like, their careers kind of just stopped with the superconducting super collider. And many of them went into finance. That was their next option. So all those like fluctuation models that are coming on, you know, all those quantitative analysts that are on Wall Street, many of them have been physicists, and mostly because of the shutdown of the superconducting super collider. So again, already there's some applications to just the theoretical work, and I haven't even gotten to the cool part, right? So how does this apply? How does like this basic science study of the strong nuclear force get us somewhere in the real world? So there's sort of two ways it happens. You build machines, and these machines have to be so complicated to test the strong nuclear force. These machines have to be so complicated that there's going to be innovations that come out of them that we see. And the human skills needed to do these studies are going to be applied to other areas in the world, like engineering or like finance. So I'm going to give you some examples of those in the last few minutes of the talk. So we'll start with the building of the machines. This is the Relativistic Heavy Ion Collider. It's in New York. It's on Long Island. It's about an hour from New York City, way out in the kind of the middle of nowhere. It's in Brookhaven National Laboratory. There's a bunch of pieces to it. The AGS is called the alternating gradient synchrotron, which was the experiment of the 70s. And now it's used as a feeder to RHIC, which is the Relativistic Heavy Ion Collider. STAR is the solenoidal tracker at RHIC, another great acronym. It's an acronym that has an acronym in it. And this is the experiment here that produced the image that I showed you on the first slide. So I won't talk too much about all the processes that go into this accelerator, but I can tell you that it was about 600 million to build, I think, and it's had couple $100 million upgrades to it. This money doesn't all come from the U.S. Like, these are huge international collaborations. Like, I think like Japan, for example, has a huge investment in this machine. This is one of the most versatile colliders we've ever built. It can do lots of stuff because it's primarily meant to collide nuclei. It can do protons, deuterons, gold, copper. I think it's even done xenon now. It's done oxygen collisions now. It can even make the beams of particles such that their spins are lined up with the direction that they're flowing. So you can do, this machine is, and it's also slated for another upgrade that could be, $1.6 to $2.6 billion upgrade to make it an electron ion collider. I think they're going to just build another ring right on top of this ring. This one's underground, actually. The sites to access it are just on this part that you can see from space. So this relativistic heavy ion collider is a great machine, but it's not even the biggest machine in the U.S. But but the other bigger machine from the U.S., which is in Fermilab, is shut down now. If you want to know about that one, you should look up like Project X for what might happen to it in the future. But the other machine that's doing heavy ion collisions in the world is the Large Hadron Collider. So if you think RHIC is pretty big, 1 kilometer in diameter, the LHC is even bigger. So you can see like the circumference of the LHC is 27 kilometers. You see this dashed line right here? This is the border between France and Switzerland. This lake in the back, that's Lake Geneva. And here, this kind of like light blue ring, that's where their old CERN accelerator is, the super proton synchrotron. That was again from the older days, and now it feeds into the LHC. The cost of this project, I think, is something like 6 billion. And but that's just the new construction. This ring, like the tunnel, already existed for a previous experiment. And so if you count all the infrastructure to make the LHC happen, it's something like 10 to 15 billion dollars. Again, huge international collaboration. It's not just one country making this happen. There's 4 experiments here. ALICE is the one that I care about the most, a large ion collider experiment, another great name. There's also a few others, ATLAS and CMS and LHCb. I'll show you kind of a schematic of some of them. But I think one of the more impressive things about this collider experiment is, okay, besides the fact that it's like deep underground, that's for radiation safety, but probably more for shielding the experiments from atmospheric radiation than from shielding us from radiation. Look at I found some information about these collaborations that built these experiments. The ALICE has almost 2,000 authors. Could you imagine 2,000 authors on a page? ATLAS has 3,000 authors on a page. And when they say students here, they mean PhD students. 175 institutions, 39 countries. 180 institutions for ATLAS, 40 countries. CMS was the only one that listed their technical staff. Like 1,000 engineers, 281 technicians, 229 institutions, 51 countries. LHCb doesn't really do heavy ions. They mostly do proton-proton collisions to produce the bottom quark. So I'll let them slide. They get to be on the slide, but I'm not going to talk about them. These are the magnets. These are the magnets that are in the ring. So this ring that's underground, already a marvel in themselves. 1,200 magnets go around that 27 kilometer ring. Superfluid liquid helium cooled. There's superconducting magnets. 8.3 Tesla. It's hard for me to describe like what a big magnetic field that is. 11,000 amp current. So this is the tunnel. This is obviously just a picture of someone working on the magnet. Also, a funny story about this one. The LHC was delayed starting for a year because a seagull like dropped a baguette on one of the power relays on the surface, and it caused like a power disruption to one of the magnets, which caused it to warm up. And so that warming up had a cascading effect that I think went 400 meters of magnets, and they all had to be replaced. And so that delayed the start of the LHC and the discovery of the Higgs by a year. But I think they spent that year making sure that everything's now seagull baguette proof. This is the ALICE detector. And I think I'm not going to go through obviously everything about it, but look at the size of it. This is the scale of a human, and this is the detector, and it's not even the biggest detector. Most of the where those tracks come from that you saw on that first slide, that would be mapped out in this region here. The TPC stands for time projection chamber. Incidentally, this part up right here, this part that's called EMCAL, the electromagnetic calorimeter, that was built at Wayne State when I was a graduate student there. And usually they don't let theorists near experimental equipment because there's an old adage in physics that as soon as a theorist comes near, all the experiments break. But I got to watch them like calibrate this with cosmic rays at Wayne State when they were building it, which was pretty cool. But I haven't actually been to the experiment bay where they actually installed it. This is where they installed it. So this is a picture of the inner detectors of ALICE. And yeah, there's a lot going on here, so I'm not going to really explain it, but it is pretty amazing to see like all the electronics and stuff that's getting developed. But look, these doors, these are giant metal doors that swing closed. I have a better picture of it. So you can see it shut. This is the bay that's underground in the ring. And so these doors shut once they slide the inner detector stuff in. And then the beam, obviously no people are here when the beam is happening. So this is a picture of ALICE, and it's not anywhere near the biggest one. The biggest one is ATLAS. I'm not gonna talk about any of it other than look at the width of it, 44 meters, 22 meter diameter, 7,000 tons. This is the inside of ATLAS, which I think is one of the coolest pictures that come out of the LHC. It's like you could drive the Millennium Falcon through this. The detectors aren't in place. This is just the housing for the magnet that will be on the inside of this. So here's a person here, right, for scale, right? I think Atlas is the most impressive one. The other one, CMS, is the most dense one. You can look at the weight of it, 14,000 tons. Mostly because it's mostly constructed with these like alternating pieces of material to absorb stuff that comes out and try and count it by absorption. There's also inner trackers in here that we are mostly used for the tracks that you see like in that first picture I showed you. But yeah, so here's a picture of CMS when they're about to like, this one is the way it's so big, they kind of like gotta slide it together. So when they're working on the inner tracking system, they're separated and there's no doors on this one. They just kind of like slide it together. I mean, 14,000 tons. I don't know how long it takes to slide together, but it's pretty crazy. So what is anyone ever going to do with this? I spent some time looking up what are the modern day practical applications of just having to build those detectors and the technology to make the magnets and the detectors. And I just stopped when I filled up the page. So I'll just mention a few. Like medical treatments is actually a big one because particle accelerators are being used a lot for a lot of medical treatments. I'll talk to you in a minute about one of my students who worked for me on a data analysis project for this project. And he's now at Duke University School of Medicine working on his PhD in medical physics. And he's actually, his PhD is on, he's using, I think, an electron beam to go through a human body and use Cherenkov radiation, which is another whole thing to talk about, that's induced by the electron beam to activate certain medicines that you could place, and then you can use the beam to activate medicines in a targeted location. There's all kinds of other ways to use the beams for cancer treatments. You actually just like kill the cancer directly. And then there's like safe handling practices for the radioactive materials. Image processing is a huge one. I won't talk about all these things. Another really big one that came directly out of CERN actually is the World Wide Web. We all use that every day. Now, the World Wide Web is not the internet. The internet is the actual connections of all the interconnected computers. The World Wide Web is the protocol for communication. So when you type www into the browser, all the programming that goes behind, original programming that goes behind making those protocols was developed at CERN actually to talk to Brookhaven. So to go from the European lab to the American lab. There's a lot of data processing software that's produced by these experiments and are now getting used in biology. So biologists might want to look up some of these. I can provide the links, but they're using these things to visualize 3D visualizations of very complicated molecules like proteins, which is pretty hard to do. Electronics, there's a lot of development that goes into making chips, like image processing chips and radiation tolerant chips that would get used for like space travel and things like that. Environment and safety, like obviously radiation protection is a thing that gets developed a lot. Nuclear waste transmutation has to get developed. Detecting certain kinds of fields and things, all of that technology has to get developed for these experiments. And there's a lot more. And like I said, I just stopped adding things to this page when I filled up the page. And this is just all stuff that comes from building the machines that, has other uses out in the world and probably wouldn't get developed at the rate they're getting developed if it wasn't for the need to make them to get these basic science projects to work. The other way of broadening the impact of this basic physics research is really just human skills. I talked a little bit about it when I talked about the finance applications of some of the math I was doing. But really, I guess I should just point out that we do the theories on the parts of the quarks and gluons, but at some point something's got to be measured, and taking the measurement and getting information out of it, that's like a data problem. So just because I'm running out of time a little bit, I'll skirt past this. But I have a modest little computing cluster, and from this I can teach students parallel computing, data analysis. This is a data analysis package that's free. C++, Monte Carlo methods, which is like a method for simulating and things like that, and Linux. I even have a student who got a job because of his use with Linux. and I have to invent, us and my collaborators, we have to invent ways of looking at the particles that come out of the detector to connect them to the theories that we have. So we have students, this is the part where the students can help us. And so Kylie was a student that worked with me. She was working on validation of some of the simulation models. We're using a model that comes out of Lund University in Sweden. And then she went on to go, and she was doing some high school teaching for a while, and now she's going to graduate school for astrophysics. Mary was a double major of robotics engineering and physics, and she worked on me with the analysis of fluctuations in the number of particles that come out of the collisions. Patrick is the only student who's following in my footsteps. He worked on the correlations of the momentums of the particles that came out with me and connecting to the theory. He's now at Urbana-Champaign working on his PhD there. Brendan is the one who went to Duke Medical School. He worked on momentum fluctuations with me and writing a code to measure those. Nolan was the one I mentioned who got a job because of his Linux experience. He's a computer science major and physics double major, and he helped me with fluctuations between the numbers of particles and the momentums that come out. And we found a lot of difficulties with this. And Mark picked it up. Mark is also a computer science major who does a minor in physics and working on his master's in computer science now at Lawrence Tech. Alec and Renali have been working on this project as part of the NSF grant with me for the past year, and I just want to give a shout out to Kyle also, who didn't work on one of these statistical observables, but he did help me with some solving of nonlinear differential equations using C++. And he was a physics with computer science major, and now he's going to graduate school to study machine learning and get a PhD in artificial intelligence. Some other quick projects, even though I'm a theorist, still have to understand how some experiments work. And I wanted to mention Cree because I mentioned in the beginning, we teach these research methods, to our students before they get to the nuclear physics part. This is Reese with his Cree project, and I let the students pick their own projects, and what he picked was making light rays rotate with magnetic fields. I'm not going to explain it all, but this was this year he did this, and this is a picture of our first setup that was like our test to see if it actually works. And so Reese is just getting started, and there's a lot of chance for him to do all kinds of other projects with me. This is another project I did with Lauren, who's an industrial engineering major and physics minor, and Morgan, who's a biochemistry major, where we were trying to measure the speed of shock waves from explosions. And I always recommend that if you're going to do explosions, you should have a chemist with you. So I'll just flash through this really quick. This was their project that they came up with, and their method for measuring the speed of the shock wave. We were trying to measure it with a high-speed camera and measuring the shock waves with recording things moving from the shock wave. One more project. I got two more projects to show you from our Cree activities. This was an acoustic levitator, so we can levitate stuff with standing sound waves. Again, I'm not an experimentalist, I'm a theorist. So we just figure it out, right? The whole process is nobody knows how to do it. Let's just figure out how to make it work. This was Alec and Renali's Cree project. And so there's an array of speakers here. And you can see this thing right here is like a dead fly that we're levitating with the sound waves. I can give you a better picture of it. Here's zoomed in. Here's our dead fly right here, just kind of hovering above these. And I even have a video of it. It kind of spins around, and we spent a lot of time trying to figure out why it makes them spin around. But you can see there's some other stuff hanging around like this. This is like a piece of the fly's wing that broke off that's kind of hovering there, and another piece of the fly that broke off that's kind of hovering there. And I'll give you a better picture of it in a few minutes. One last one to tell you about another Cree project. There's a poster on this one at this research day. This is Andrea. I'm sorry for the derpy face that I have in this picture, but this was a project about visualizing small changes of index of refraction. So you can see actually turbulent airflow with this setup. And again, I won't explain it, but we got some really awesome images from it. So you could see like you could pick where's the density increasing and decreasing in air from hot objects. You can even do cold objects. So we put the levitator in front of it, and you can actually see the standing sound waves. Like these standing sound waves are like the interface between the blue and yellow is like the peak or trough of the high pressure, low pressure parts of the sound. And we even have a video of this one. This is the fly sitting in the standing sound wave being supported by this high pressure zone right here, which is pretty awesome. So if you want to know more about it, you can go to Andrea's poster. That's one of the, she's got a video about this at this research day. And so, okay, what is anyone going to do with all of this stuff? What is anybody going to do with basic science study? This is us, right? The strong nuclear force. I think the strong nuclear force is going to be the 100 years from now future of our technology. And already it has just studying it is bringing up important advances that have modern uses. And the training that it takes to study these things might be the biggest impact we have. Like, what are you going to do to study nuclear physics? You're going to become an engineer. You can become a computer scientist. You can become a physicist who solves medical problems. By the way, Andrea, I think this is her ambition, is just like Brendan's ambition is to use physics to solve medical problems. Patrick is going to be a nuclear physicist. Kylie's going to be an astrophysicist. We're going to have the influence with biochemistry and astronomy. I think that's the future for both Alec and Renali. And Reese, the future's open to you. What are we going to do? What are we going to do with physics? I think you're looking at what we're going to do with it. So I think that's it for me. I thank you so much for giving me the opportunity to show off a little bit, and I hope you enjoy the rest of Research Day.
Thank you so much, Dr. Moschelli. And I want to thank everybody for joining us this year at the 8th Annual Research Day virtual conference that we're having. And I would encourage you to please contact Dr. Moschelli directly. You see on the screen here his email address. And at this time, we are going to conclude our keynote address. And I would like all of you to please visit our Research Day webpage. You see here on the screen, here's the address. Pretty simple, just type it in your browser and you will be able to access the webpage, and you will see all of the presentations this year. There's about 70 of them, and I'm very excited, and I appreciate all of the students and faculty who have submitted their presentations that I've organized on the web page. What you'll see when you go to the web page is you'll see a YouTube video that is of each presenter's presentation, as well as, if it's a poster, a link to their poster. And then you'll see at the beginning of the web page, I'm asking for LTU faculty and formal faculty to please register to be a judge to evaluate the 29 posters, because we have a poster competition this year thanks to the HHMI grant to provide funds for that. And we're also, some of the presenters had requested for their presentations to be evaluated under a new category called entrepreneurial potential. And I want to thank Mark Bruckey to help organize that. And that judging is happening separately through Mark Bruckey. So if you have any questions, please do not hesitate to contact me, Matthew Cole, mcole@ltu.edu. And I want to thank Dr. Modgill and Dr. Sobe. And I see Dr. Modgill has his hand raised. So yes, please, Dr. Modgill, please do not hesitate to share.
Matt and George, I think this was an immensely interesting seminar or lecture. Your ability to show nuclear physics and its relevance to society, the medicine and treatments, is an amazing project. And these young people who work with you, they have a great future. You need the high intellectual nuclear physics people who are doing the enormous work beyond the imagination of human mind. This was a very, very good presentation. Congratulations.
Thank you very much.
Dr. Sobe, would you like to make any concluding remarks?
Absolutely. Thank you so much, George. This has been really inspiring. I personally learned a lot, particularly the piece about the applications in the upcoming future of the technology and your research. Thank you for a great presentation, and we look forward to more excellent work of truly great impact from you and your students. Thank you all for attending, and thank you, George. Thank you.
Thank you very much, everybody. And George, we'll leave you with one question from our colleague in biomedical engineering, Dr. Meyer, who asks, when are we going to get a grand unified theory? I'm not sure you can give us that answer in a few minutes, but
That's going to be a tough one. But you know what I always think about something like that is, if you want to win a Nobel Prize in physics, what you got to do is like go to the fringe of math and figure out, is there a part of math that just hasn't been used yet in physics? And you'll find it. It's going to be in physics somewhere. And I think that's probably the step that's going to have to be taken for that one.
okay, well, with that, we have recorded this, so we can revisit this and we can look again, and we'll pass it on to our colleagues who are not able to join us today. Some are teaching, some are doing labs, and we want to thank all of you for attending this presidential colloquium, the 8th annual Research Day. As a reminder, we started this 9 years ago, and we rotate through the colleges. The first keynote address was Dr. Stavros in College of Business. And when you visit the Research Day website, you will see all of our presenters over the years. We've had Dr. Stavros in business, Dr. Carpenter in engineering, Dr. Geyer in architecture, Dr. Shamir in arts and sciences, Dr. Kim in architecture. By the way, Dr. Kim and I were the two who started the Research Day originally in 2013. So special shout outs to Dr. Kim, Dr. Castelli from business in 2018, Dr. Flescher in 2019. And this year we were so excited to have you, George, to be our 2021 keynote speaker. And thanks again to Dr. Modgill and Provost Sobe, and wish you all a happy Research Day, and please enjoy your viewing of all the presentations at your leisure. This year, it's asynchronous, so you have plenty of time to click on each YouTube video and watch them. And our plan is to have the judging done so that next week, Monday, we can post the winners of the poster competition. And our plans are in the future to have more competitions like this for other than just the posters. We'll add in there the papers as well. So thank you very much, everybody. And
Thank you.
have a wonderful day.
You too.
Thank you.